All right. So, all right. So, what we're going to talk about today is a topic that you guys should all be familiar with: partial differential equations. So, a lot of this stuff is going to overlap with the stuff you guys already did about with ordinary differential equations. There's just going to be a few things here that are going to be different. And so a lot of what I'm going to do is really highlighting the differences between PDEs and ODEs and how that changes how you solve them. And then one thing we're going to get into, which is going to actually lead into next week's talk on special functions, is going to be separation of variables. And so the idea is that we can, in some ways, the stuff from PDEs is going to just dovetail directly into the stuff on special functions, and you'll get a chance to see a little bit more about what those involve. And one thing is that next week, for the talk on special functions, it's a lot of information to go through, and so I'm going to kind of change up the format a little bit for next week. And instead of doing exactly what I'm doing now, I think what I'm going to do is like actually have you guys print out the notes, or maybe I could copy the notes for you guys, and we'll just go through them that way. Otherwise, what I found is that there's so much on special functions as far as material-wise, it's hard to get through all that in one block, one 3-hour block. It's just a lot. And the thing is that as far as the level of challenge of the concepts we're going through, I think that this is probably conceptually the hardest thing we're going to do for the rest of the semester. The special function stuff is not as difficult. The probability and statistics is, most people think that's pretty easy. And we're going to actually be meeting the week of Thanksgiving, at least on that Tuesday, because I'm going to be out of town on the 1st. And so we can use that time to go over the review for the final, and then when we come back, we can actually do a little bit more review before the final. So we're getting towards the end of the game here.
Are you going to be available email-wise?
Oh yeah, yeah, I'm going to be available. I'm always available email-wise. So it's just that I got something about save the date for an invited talk in San Antonio on the 1st, so I guess I'm on the list for that. And then it's just a matter of getting all the rest of the details. So I'm assuming that that's still going through and that they still want me to come out there. But that's pretty much just going to be a day trip. It just happens to be on a day that we have class. All right, so we're going to be talking about partial differential equations, PDEs. And so an example of basically what a partial differential equation is it's a differential equation, but it has more than one independent variable. So an example of that is the 1D wave equation, where you might have something like this. Where this is just a 1D scalar wave. And what you'll notice in going through this is that pretty much every example I'm going to give you of a PDE is going to be a second order equation. And the reason why we're doing that is because if you look at your physics equations, most of the laws of physics are basically second order differential equations. For example, and the reason why is because, force, if you're talking about writing laws of motion and things like that, it's usually a force equation, and the force is second derivative of potential of position versus time. So it's just kind of natural. Everything's going to be a second order differential equation. Also, just to keep things simple, we're only going to be using linear. So these are only going to be second order linear. examples. Now, there are, of course, nonlinear examples we could have, but this is, just for learning purposes, this works. Now, in this equation, c here represents the speed of the wave, which you could think of as the speed of the wave is given by the tension divided by the linear density, gives a speed squared or something like that. So this is one example, 1D wave equation. Another example is Laplace's equation. And that is the Laplacian of psi, which in Cartesian coordinates is a derivative, second derivative of psi with respect to x, plus second derivative of psi with respect to y, plus the second derivative of psi with respect to z, equals 0. Okay. I'm not going to use the Poisson equation, but that's very similar to Laplace's equation. Then there's a 3D wave equation, where this might be like taking the Laplacian of psi minus 1 over c squared, second derivative with respect to time. And so you can see each one of these depends on at least 2 independent variables. There's a diffusion equation, which is the Laplacian of psi minus 1 over kappa partial psi respect to t equals 0. And you can see that looks a lot like the wave equation. The only difference here is that this is a first derivative as opposed to second derivative. And here, kappa is known as, it's essentially just a constant here, and it comes from taking the heat conductivity and dividing it by the specific heat times the density, just as an FYI. And then you've got the Schrodinger equation. And the Schrodinger equation is minus h bar squared over 2m, the Laplacian of psi, plus the potential as a function of position, psi, equals I h bar time derivative of psi. And then there's a time independent form, and in the time independent form, they take psi is proportional to e to the minus I e t over h bar, which basically says that you're assuming that you have a solution that oscillates with time. And that implies that you now have the Laplacian of psi plus 2m over h bar e minus v of x psi equals 0. And you can clearly see that these are all differential equations. They're all second order. You can see in the case of Schrodinger's equation how you put in some boundary conditions on that, and all of a sudden you've got a eigenvalue problem, which is how quantum mechanics works. And also, when I say linear, what linear means is that if you have two solutions, psi 1 and psi 2, then that implies a third solution, psi 3, which is equal to psi 1 plus psi 2. And so you can literally just keep adding up solutions and getting other solutions to your problem. So these are all what we talk about when we say partial differential equations within physics. And so you can also have inhomogeneous examples, like all these are homogeneous in this case. But an inhomogeneous one would be something like taking your wave equation and setting the other side equal to minus 1 over t f of x and t. And then if you have an inhomogeneous example, you could solve it using a Green's function, just like you did with the ordinary differential equation. So what happens, though, that's going to be a little bit different when you're talking about these partial differential equations is that we're not just solving it for one variable. And because we're not just solving it for one variable, there's a lot of other things that can happen with these guys that you don't see with the partial differential equations. And particularly, one big difference is going to be the boundary conditions. And boundary conditions, I'm going to abbreviate this as just BC a lot. So if you see me do that, that's what I mean. And in order to solve the differential equation, you have to have some kind of boundaries that you have to apply to it. And there are basically 3 different classes of boundary conditions for PDEs. All right. The first are called Dirichlet. And the idea of the Dirichlet boundary conditions is psi is specified at the boundary. An example of that is like when you're trying to solve Laplace's equation in electromagnetism, then what happens is you're given what the potential is on each of the boundaries, and then you can calculate what the potential is everywhere else, given what it is on the boundary. Another example of a condition are called Newman conditions. And the Newman conditions basically say that if you take the derivative of the solution with respect to the normal at the boundary, that is given. So in other words, you don't necessarily know what your solution is, but you know what the derivative of your solution is at the boundary. Which sounds a little odd, but it actually makes a lot of sense in some ways, that you know how it changes. And then finally, there's something called the Couchy conditions. And the Couchy conditions means you have both the solution and the normal derivative of the solution are given. And so you have to have one of these conditions in order to solve your differential equation. Yeah?
Now, this is where we're only hyperbolic equations for the constant.
Yeah, and we're going to get to that. Yeah. Yeah, so we're going to get into all that stuff soon. Yeah. So the idea.
So is a Couchy like implicitly solvable by one of the other two differential?
I'll get into that.
Okay.
And how, you know, so part of the whole trick to differential equations is knowing that given which one of these you're dealing with, what boundary conditions do you have to use in order to solve it? And I mean, and that is the real challenge here. I mean, that's pretty much 90% of the job. So what we have to do is we have to figure out how to classify these things. And then once we know how to classify them, then based on a classification, we can choose which boundary conditions to apply. And then from there, it's just like dealing with ODEs. And there's ways of dealing with them, like separation of variables, which I'll talk about later, where you're literally taking your PDE and turning it into an ODE, solve it. And if you can't do that, then this is where our computers come in. Because numerically, I could solve any of these things given a computer. It's just a matter of, on the computer, I have to know what kind of equation I'm dealing with, and then I have to know which boundary conditions apply in order to solve it correctly. So everything kind of comes back to, now I've got 3 classes of boundary conditions I could possibly use. What do I do? Okay. So the way to think about this, and I think this is from, I'm trying to think if this, what I'm going to give you is from Matthews and Walker, or if it's from the other one. I think, yeah, this is from Matthews and Walker, about Arkin and Weber. And the basic idea here is that, let's suppose you have a curve. Okay? So this is y, and this is x. And so within y and x, you have some kind of curve that looks like this. Everything under here is sort of your, is where your solution space is. And what's happening is, this is a PDE, which is a function of y and x as independent variables, and it gives you some solution. And so this is the boundary to your solution space, or where your problem is. And so at the solution, you have a normal to the boundary here, in hat. And so what happens is, you could say that, well, x is a function of s, where s is this arc that moves along the curve, and so is y. And so we can say that, well, the normal derivative at the boundary is given by taking the derivative of the solution with respect to x times the derivative with respect to y. Whoops, it should be s. Derivative of y with respect to s, and then we throw in a negative sign here, because, well, you can see that the solution is going to go negative with respect to x here. And then I'm going to add to that the derivative of psi with respect to y, and the derivative of x with respect to s. So what this is telling us is, we have the change in the solution with respect to x times the change in y with respect to s, plus the change in psi with respect to y times the change in x with respect to s. And where this comes from is basically the normal, the unit normal, is really equal to minus dy ds comma dx ds. As in, what this means is that if you look at this unit normal here, it's pointing in the negative x direction with however it changes with respect to y, or y changes with respect to s. And it's pointing in the y direction as x changes with respect to s. Does that make sense? And so what they really did was they said, well, if you take the unit normal and you dot the unit normal, actually, we take del of psi and we dot that with the unit normal, okay? Then what that's really doing is it's saying we're going to take partial psi with respect to x, x hat, plus partial psi with respect to y, y hat. And then all of this is being dotted with minus dy ds in the x hat direction, plus dx ds in the y hat direction. Okay? And so if you dot all that together, you get n up here. And so the result of that is going to be minus partial psi with respect to x dy ds plus partial psi with respect to y dx ds. Everybody got it? So all of this is n. So what's happening is then that this is our normal derivative at the boundary. And so if you take d ds of psi of s, then what you're doing is you're taking the derivative of psi with respect to the arc length. And so this is equal to partial psi with respect to x dx ds plus partial psi with respect to y dy ds. Because really I'm taking a derivative with respect to s, but psi doesn't depend directly on the arc length. Psi depends on x or y, so that's why I have to go through all this. Now, you'll notice that this sort of implies that the partial psi with respect to x is equal to partial psi with respect to x times n hat squared, right? Where what's happening is n hat squared is equal to 1, so this works. And so n hat squared I can get from taking this thing and squaring it. And so that is equal to partial psi with respect to x times dy ds squared plus partial psi with respect to x of dx ds squared. And what I can do then is I can even take this and expand it out by just simply adding and subtracting cross terms. And I could say, well, I can also add to this minus partial psi with respect to y of dx ds dy ds plus partial psi with respect to y of dy ds dx ds. And so I added all these extra terms because now what I can do is if I look back here and I'm comparing what I just got here to what's up here, I can say, well, if I take minus n of s and I multiply that by dy ds, then you can see that I end up getting a d psi dx times dy ds squared, like this first term. And then I also have minus d psi dy dx ds dy ds, which is this term right here, the third term. So those two terms are basically wrapped up in here. And then for the other ones, I've got these two where this is d psi dx dx ds and then d psi dy dx ds times dy ds. So that is basically like saying d ds of psi of s multiplied by dx ds. So effectively, I've gotten the partial of psi with respect to x written in terms of derivatives, either the derivative with respect to the normal of my solution, or the derivative of my solution along the arc length, where I'm multiplying 1 by dx ds and 1 by dy ds, right? So it's kind of like I'm saying I can take my first derivatives of how this thing changes with respect to x, and I'm parameterizing it by the other derivatives of the curve. And I can do the same thing with partial psi with respect to y, and say that that is equal to n of s dx ds plus d ds of psi dy ds. So I just did that basically just because I wanted to show that if I know what's going on with this curve, I can, as far as how the curve changes or how the solution changes as I move along either the normal or along the curve, then I can find out what the derivatives with respect to x and y are, right? So that's all that's saying. Now, you can do the same thing, but instead of doing it for first derivatives, you could do it for second derivatives. So for second derivatives, you've got second derivative of psi with respect to x squared. You've got the second derivative of psi with respect to both x and y. And you've got the second derivative of psi with respect to y only. And so what you can do is you can take the first derivative terms here, and you can just differentiate them again in order to get these three terms. And when you do that, you have d ds of partial psi with respect to x is equal to the second derivative of psi with respect to x dx ds plus the second derivative of psi with respect to x and with respect to y of dy ds. And then you've got the same thing, but for the derivative with respect to y. And so you've got the second derivative of psi with respect to x and y, dx ds, and the second derivative of psi with respect to y, dy ds. And so what happens here is you have two equations here, and you have three unknowns. The unknowns are basically, you have all three derivatives, second derivative terms. And so what you can do is you can throw in a third equation. And the third equation is your original differential equation, which is something in general form, it looks like this. All right, and so this is basically the most general form with which you can write any of those differential equations I showed you on page 1. Because if you think about it, every single one of these equations you can basically write as if there was an A term, a B term, a C term, and in some cases, where is it? in some cases, you could see that this is the inhomogeneous part at the end. So what happens is you got these equations, and you're basically going to create a matrix out of them. And you're going to say, well, if I create a matrix where I'm going to have the first column is going to be the second derivative with respect to x. The second column is going to be the second derivative with respect to both x and y. And the third column is going to be the second derivative with respect to just y. And you can see I have the other terms that are missing here. So this first line here is going to be ds partial psi with respect to x. The second one is going to be ds partial psi with respect to y. And the last one is basically going to be f of all this stuff. Okay, so basically that's the f of x. And so now I fill in the gaps, and I have essentially this is, if you look at this first term is going to be dx ds. Second term is going to be dy ds. Third term is going to be 0. And then I go to this equation, I have 0 dx ds. And then I have dy ds. And in the last one I have a, b, or 2b, and c, right? And so the idea then is I want to solve this matrix in such a way that the determinant of the matrix is going to give me 0. And what happens then is that's basically saying that you don't have, when the solution goes to 0, when you have that 0 solution, that's where effectively you get no solution existence. It's kind of like looking for the danger spots. And so what happens is you can, easily solve this matrix because it's not a complicated one. But what you'll get is that a times dy ds squared minus 2b times dx ds dy ds plus c dx ds squared equals 0. Should be that solution. It comes from this, right? And so what happens is this is basically going to determine the two directions at each point in the xy plane where we have what we call characteristic points or characteristics. And what happens is at these points you really don't have a solution. So it's basically saying if we could solve the equation for dx ds, dy ds, where these characteristic points exist, then that's going to tell us that if we're at that point, then we run into a problem. And we have to avoid those parts. Now, if we use the quadratic equation on this, we could see that dy ds must be equal to 2b times dx ds plus or minus the square root of 4b squared times dx ds squared minus 4 AC times dx ds squared, all divided by 2a. And then dx ds is equal to 2b dy ds plus or minus the square root of 4b squared dy ds squared minus 4ac dy ds squared divided by 2c. So it's basically flipping the equation around. So the reason why this is significant right here is because if you have this equation satisfied, where this goes to 0, which is satisfied by these quadratic equations, then what happens is the determinant of this matrix is 0, which basically means that you do not have a solution to your differential equation, right? So what we see is that at those points our solution doesn't exist, so we have to avoid these things, which are the characteristics. Because solutions to second order PDEs do not exist if the boundary curves lie on these characteristics. So what this means is that if you can set what A, B, and C are, you can see that depending on what A, B, and C are, is whether or not these characteristics are real numbers. And if they're real, then they might exist. And how many exist depends on, different things. So like, for example, let's suppose you have B squared greater than AC, or greater than or equal to AC. Then you could see here that since there's a 4 on both of these, and there's a dx ds squared on both of these, that if B squared is greater than AC, then you get a real number in this radical. And a real number in a radical means that this whole thing is going to be real. It's not going to be complex. And therefore, you can have a real characteristics. So in this case, you have characteristics that are real. And if characteristics are real, and if your boundary happens to lie on these characteristics, then you don't have a solution. And so what we do is we say if B squared is greater than AC, then we classify the PDE as hyperbolic. And if it's greater than AC, then you could see that you have a number here which is real, and there's a plus and a minus, so you end up with two characteristics. So in other words, there's two different solutions that you have to avoid in order for this. And I'll get into more realistic terms about what this means in a few minutes. If B is equal, or B squared is equal to AC, then we call this Pde Parabolic. And parabolic means there's one characteristic. Because you can see there's a 0 here, and so you have one number, that's it. And if B squared is less than AC, then we call this elliptic. Because now you got the square root of a negative number, so this is complex now. And so it's not real, so therefore no characteristics, no real values you can lie on. And so based on what A, B, and C are is going to determine whether or not you have a real characteristics you have to avoid. And if you have to avoid characteristics, then that tells you you have to have certain boundary conditions in order to avoid those characteristics. And if you don't have to avoid the characteristics, you can use different boundary conditions. So elliptic equations in some ways are going to be much different way how you solve them than hyperbolic equations or parabolic equations. So let me give you an example of one of these suckers. And this is a simple hyperbolic equation. And so what happens is, let's say A is equal to 1, B is equal to 0, and C is equal to a negative value. Then you can get partial second derivative of psi with respect to x minus 1 over c squared second derivative of psi with respect to t equals 0. So this is basically the wave equation, right? And you could see that there's no cross term, so b is equal to 0. And one of these has got to be negative. Either a is negative or c is negative. So when you multiply a times c, you're always getting a negative number, which is less than 0. So therefore, it's always hyperbolic. Now, before we go any, let me finish this example, and then I'll go back and talk about some of the other ones. So the reason why this is important is because if you throw in the characteristic equation, and the characteristic equation comes about by basically taking your A, B, and C and plugging it into this equation. So it's the equation that defines the characteristics. Then you have dt ds squared minus 1 over c squared dx ds squared equals 0. Okay, so that's just basically solving the characteristic equation. And then you could see that from this equation you could get a very simple equation, dx dt squared is equal to c squared, which tells you that basically if you're moving, in physical terms what this means is if you're moving with the velocity of the wave, then you can't see the wave. So if you can imagine that for a second, like, imagine a surfer, and if you're just on the water and you're just sitting there and the wave comes up and down, you'll go up and down with the wave, right? But if you're surfing with the wave and you're moving with the wave, you don't see the wave. What you see is just you're moving along on this thing, and you don't really see the whole wave structure. You only see the wave structure when you actually are affected by something going up and down. So there's basically saying is that, like, you cannot create boundary conditions for your wave equation which move with the wave. It doesn't work. And since there's no, this is both squared, it basically says your two characteristics are one moving one way and the other moving the other way. So in other words, you can be moving, if you're moving at the same speed as the wave, then you're just not going to see the wave. So if you look at this, you can get some simple solutions to this. One is going to be x minus ct is equal to some constant we're going to call zeta, or x plus ct is equal to a different constant called eta. Each one of these corresponds to a physical system traveling at the wave's velocity. They're both solutions to this characteristic equation. And so if you graph it, it basically looks like if this is x and this is t, then you have either this constant zeta or this constant eta. So now, what happens is that these characteristics form a natural set of coordinates. So, if you take eta plus zeta and you divide by 2, you get back x. If you take eta and you subtract zeta and you divide by 2c, you get back t. And so you can rewrite your differential equation using these as, instead of having second derivative of psi with respect to x minus 1 over c squared, second derivative of psi respect to t squared equals 0, you can rewrite the equation as the second derivative of psi with respect to eta and zeta equals 0. And you know what? This is still a hyperbolic equation, because here b is equal to 1 and a and c are equal to 0. So b squared is still greater than ac. So basically I just rewrote the partial difference equation using different variables. And I can also use this to say, well, psi is equal to f of zeta plus g of eta, which is a solution of this differential equation. And if I take the solution where t is equal to 0, then that's going to become f of x plus g of x. And if I take the time derivative of that, I'm going to multiply by 1 over c, x and t equals 0, then I get minus f prime of x plus g prime of x. And the reason why there's a negative here is because, remember, my normal derivative is equal to 1 over c partial psi with respect to t. So this is effectively my normal derivative at the from before. And so I just took a derivative with respect to time, and then and then just took time equal to 0. So let's see. So then what happens is, well, I could say, well, f of x is equal to psi of x at t equals 0 minus g of x. And then I could say f prime of x is equal to g prime of x minus 1 over c partial psi respect to t. And then this, in turn, can be written where f of x is equal to my g of x. And then I could just integrate this guy in order to get my psi term. So I have this as minus 1 over c, second integral partial psi with respect to t, where I'm integrating it with respect to x. So in other words, what I did was I took this equation here, and I just integrated the entire equation and compared it to what's going on here. And so if you compare these two equations, what you can get then is that f of x should be equal to basically adding these two together and dividing in half. So you have 1/2 psi of x minus 1 over 2c integral of the time derivative of psi dx. And g of x can be solved in basically the same way. And so what I just did here was basically I solved for what's happening at one of the boundaries, the t equals 0 boundary. And so I said, well, the t equals 0 boundary, I have the solution at the boundary, I have the time derivative or the normal derivative of the solution at the boundary. And either one of those basically gets me back to, I can solve for f and g as being in terms of the solution and the normal derivative of the solution at the boundary. And so because of this, it looks like I need Couchy conditions in order to solve this. And so to be a little bit more complete, if you have a hyperbolic differential equation, then what happens is you need to use Couchy conditions, and the boundaries are going to be open. And the reason why I say open is because you need to know what the solution is at the beginning, but not necessarily at the end. So what happens is a system, you have to set the initial conditions for it, and it freely evolves, but you don't have to know where it's going to end up. So you can evolve it in time. And you can get that from how this works with having to specify the solution in x and how it's going to change with respect to time. Now, if I had done elliptic, and I could do, and you basically go through the same process, what you'll see is you can use either Dirichlet or Newman conditions. And you'd use closed conditions. And an example of that is you're solving the Laplace equation. You need to know what it is on all the different corners of the box, or their derivatives. So you can have either know the potential on all the walls, or you can know the electric field, which is the derivative of the potential, right? You don't need to know both, but you have to know them on every side. So that's why we call it closed.
You had a homework problem here with sphere.
Mm-hmm. Or parabolic. And parabolic also uses Dirichlet or Newman. And these are open. And the reason why I guess these two would be open is because you do have the characteristics. Somehow that affects how that would work. And so what I like to do, I want to go back to the first page and ask you guys, first equation here, 1D wave equation, hyperbolic, parabolic, or elliptic? Nope. Hyperbolic. Because remember, A is 1, B is 0, C is negative, because you have to kind of move this over to the other side. Okay, what about the Laplace equation? Hyperbolic, parabolic, or elliptic?
That's elliptic.
Yeah, that's elliptic, and the reason why is because there's no cross term, but if you look at x and y, or x and z, or however you choose, since they're all basically the same, treated the same here, they're all, you're going to get A times C greater than B. Okay, anybody else for the 3D wave equation? What? Yeah, still hyperbolic. And this is kind of one of these tricky things with these, is that whenever you see the Laplacian and you see like a time dimension in here, you have to actually treat this as if time is separate than all these other dimensions and treat it like these are one dimension and this is another one. It's hyperbolic. What about the diffusion equation? What? No. What? No. Anybody else? One left. Yeah, it's parabolic. This is a tricky one, and the reason why is because the way I look at it, you got your spatial dimensions and you have your time dimensions here, right? So you have to use basically, let's say, x and t. And so what happens is c is equal to 0 because there's no second derivative with respect to time. There's only a first derivative. But here you have a second derivative with respect to your space, and there's no cross term. So therefore, it's 0 equals 0, which is parabolic. So you would actually, if you worked out the characteristic equation for this, you would get one characteristic. Oh boy.
Why is C 0?
Why is C 0?
Yeah.
Oh, because there's no second derivative with respect to time. It's only a first derivative.
Oh.
Okay. What about Schrodinger equation? The non-time dependent, or the time dependent one. Yeah, that one's also parabolic. Because again, there's no cross term, and you could see that C is equal to 0, and so you can always argue that 0 is a 0. What about the time independent Schrodinger equation? Anybody else? Nope. Elliptic. Because if you look at it, all the derivatives are spatial, since there's no time dependence. So now here, it's just this term only. So here's the neat thing, is that, and this is why you have the time independent Schrodinger equation, because instead of having to solve a parabolic equation, you can solve an elliptic equation. And you can use closed boundaries. If you think about quantum mechanics class, if you're trying to solve the time independent Schrodinger equation, you're solving it by specifying all the boundaries, right? And then solve it. So you're solving it like an elliptic equation. If it was a time dependent Schrodinger equation, it would be open boundaries. So you'd have to specify what the thing looks like initially and let it kind of evolve. So this is one of these little tricks that people are doing in physics that they don't really tell you about, is that they're basically doing stuff like changing a parabolic equation into an elliptic equation so it's easier to solve, and they're getting a solution that works in those situations. It's a lot easier to come about than the other solution. So anyway, I think guess that equation's a fun game. Encourage you guys to play the home version. All right. So we got one more thing, and then we're done for the day. And this is not the longest lecture of the semester, obviously, but I think that we cover all the really important stuff. And like I said, next week it's kind of the natural break of where we're going to end up with next week when we start talking about special functions, because this is going to actually introduce some of the special functions that we're going to talk about next week. And only that way we're going to go about it a different way. So, this is separation of variables. So the idea is that now that you know, if you were solving these things numerically or other means, you know how to pick the boundary conditions, you can understand different types of equations. The idea of separation of variables is to find a way to solve your differential equations, your partial differential equations, by turning them into ordinary differential equations. And if you turn them into ordinary differential equations, then they're a lot easier to work with, because you already know all the tricks for solving those guys. So you have, for example, Laplacian of psi minus 1 over c squared, second derivative of psi with respect to time equals 0. It's the old-fashioned wave equation, but we're doing it in 3D. So the way that this works with separation of variables is you're going to try a solution, just like we did before, and where you're going to break it up and assume that you can have two parts of the equation, one which depends on position and the other one which depends on time. And if these two parts of the equation are completely independent of each other, there's no cross terms. And so this is something that only works if you're talking about linear equations. In other words, this, if you're trying to solve Einstein's equations, this is not going to work for you. But you try to solve a wave equation and it works pretty well. So you take this solution you're trying and you plug it back into the differential equation. And one way that you can see that this is possibly going to work is that there's no b term. So there's nothing where you're taking derivatives with respect to both x and t. It's just one or the other. And what happens is you get that the Laplacian of the x term divided by x is equal to 1 over c squared times 1 over t times the derivative of the t term with respect to time. And so everything on the right depends on time, everything on the left depends on position. And so that's why we say that these things are separate. And if they're separate, then you could say that they're both equal to a constant, because if you change time but you don't change position, then it shouldn't affect the other side of the equation. So they must both be equal to a constant. So we say that constant is equal to k squared. And so you could see then that minus c squared k squared, which we could say is equal to minus omega squared, is equal to 1 over t times the second derivative of t with respect to time. And so that translates into the second derivative of t with respect to time plus omega squared t is equal to 0. And this gives you that t is equal to e to the plus or minus I omega t, or something like that. So that's just a simple solution so far. Now, we also know that minus k squared should be equal to del squared x over x. And so we see that minus k squared x is equal to del squared x, like this. But this is not just a function of x. This is a function of position. So we have to assume some kind of coordinate system. So we're going to say spherical coordinates here. Partially because spherical coordinates means that we really get deep into this thing. I could have done Cartesian coordinates and it'd be much simpler, but we're doing spherical. And so on the spherical coordinates, what happens is your equation right here is going to become the Laplacian, which is 1 over r squared partial respect to r of r squared partial respect to r plus 1 over r squared sine theta partial respect to theta of sine theta partial respect to theta plus 1 over r squared sine squared theta partial second derivative with respect to phi squared of x and all this plus k squared x is equal to 0. All of this just came from the stuff I just did, and spherical coordinates. So all this comes from this. Now, x in spherical coordinates is going to be r of r plus theta of theta and phi of phi. Or sorry, these aren't plus, these should be times. Sorry about that. So all these are supposed to be times each other. With the idea that, you know, your solution is all the other solutions is multiplied together. So when you take this long thing here, you plug in the x values, then you get 1 over r squared r, because I just multiplied in the whole thing and then I divide it by the solution, of d dr of r squared dr dr plus 1 over r squared capital theta sine theta d theta of sine theta d theta plus 1 over r squared capital phi sine squared theta of the derivative of phi with respect to phi plus k equals 0. All right? So when you look at this, what happens is you can see that the first term only depends on r, but there's r's scattered out throughout this whole thing, so it's not quite that simple. The second term depends on theta with no phi dependence, but there's an r here. And the last term, you could see that there is basically it's just phi, and there's a theta and an r term in there. So what we could do is we could say, well, ignoring the r squared and the sine theta, we can just say, well, everything else here is a constant. So d squared phi, d phi squared, times 1 over phi is equal to a constant called m squared, or something negative m squared. And so the reason why we chose that was because when you multiply it out, this gives you the differential equation, second derivative of phi with respect to phi plus m squared phi equals 0. And the solution to that is just going to be phi equals e to the plus or minus I m phi. Simple solution. And because this is a solution, we can replace this part here with just m. So now our equation, what we could do is let's multiply the whole thing through by r squared, and we get 1 over r d dr of r squared dr dr plus 1 over capital theta sine theta d theta of sine theta d theta plus all of this is just going to be minus m squared. So actually you want a minus sign here. So I have minus m squared over, I guess, sine theta, sine squared theta. And then I have my k times r squared equals 0. Or sorry, k squared times r squared. Lots of squared there. And so you can see here, I've eliminated phi as a variable, and I've eliminated time as a variable. So what happens here is, if you look at this, these two terms right here only depend on theta. And this first term and the last term depend on r, right? Well, this equation, 1 over sine theta d theta times the sine of theta d theta minus m squared over sine squared theta must be equal to a constant times theta. And so we're going to call that constant minus L times L plus 1 theta, which has got to sound like the weirdest constant I could think of, right? And the reason why we picked that is because if we compare that to the solution to a Legendre function, or Legendre's equation, where you might have something like, let's see, 1 minus x squared times d squared theta, d theta, or dx squared, minus 2x d theta dx plus L times L plus 1 minus m squared over 1 minus x squared theta equals 0. This solution to this is equal to PLM of x, or QLM of x. And these are associated Legendre functions. And it works if x is equal to cosine of theta. So if x is equal to cosine theta, then the solution of all this is just these functions that mathematicians have known about for years. And so that solves basically this whole big chunk of the equation right here. So now your function becomes, what's left is just going to be 1 over r squared dr of r squared dr plus k squared r is equal to L times L plus 1 over r squared r, which is only a function of r now, which is what the goal was. And so if we do a change of variables, we take r and we turn it into u over square root of r, then we get the equation d second derivative with respect of u with respect to r plus 1 over r du dr plus k squared minus L plus 1/2 squared over r squared u equals 0. And this is actually Bessel's equation. And so the solution to that is a Bessel function. R is equal to JL plus 1/2 of KR over square root of R, or YL plus 1/2 KR over square root of R. And so these are actually, when you're putting in these halves, these are actually known as spherical Bessel functions. And so we call a spherical Bessel function where you have something like J sub L of x is equal to square root of pi over 2xj of L plus 1/2 x, and n x of L is equal to square root of pi over 2x y L plus 1/2 x. And so what happens then is that when you put all this together, then your solution, R of a psi of R, theta, phi, and t, is equal to essentially, well, I guess you could have some coefficient of L, M, and I guess that would be it. Yeah, it's L and M of J, L, of K, and R, e to the plus or minus I omega t, e to the plus or minus I m phi, and then either a p Legendre polynomial or a q. And which one you end up with probably depends on the boundary conditions. No, this is not spherical harmonics. This is a spherical Bessel function. What? Oh, with here? Yeah, these are spherical Bessel functions. You know, so we'll talk about that a lot more next week. But essentially, they're what come out of the Bessel's equation when we're doing it in the spherical coordinates. So anyway, the whole idea of this is just that these special functions, you can kind of get to them through using the separation of variables and the different coordinate systems. And so we're going to go deeper into that next week. And like I said, it's a lot of details and stuff to cover. And so I'm going to do that lecture a little bit differently than we have been. But otherwise, I guess, you know, let me know if you have any questions. You guys have a homework to work on, and also if there's any questions on the homework that I handed back, we can deal with that on Thursday, or if you want to just email me before then. Okay. All right, I'll see you guys.